In 2023, researchers at MIT confirmed something that shouldn't be possible. Roman concrete, mixed 2,000 years ago, is actively healing itself, right now, today. While modern concrete starts cracking within decades, the Roman version absorbs moisture, grows new minerals inside its own fractures, and gets stronger. One structure. In the rainforests of northeast India, bridges are growing, not deteriorating, growing. Their primary building material is still alive, still fusing, still adding strength every single season. Modern engineers have been studying them since 2019. They cannot replicate what they found. And every June, in the Peruvian Andes, 1,000 people gather to destroy a working bridge on purpose, then rebuild it from scratch, by hand, in 3 days. No machines, no modern materials. The same technique their ancestors used 600 years ago. 3 structures, 3 different civilizations, no contact between them. And every one of them is doing something modern engineering has spent years trying to understand, and in several cases still cannot copy. There are 7 of them on this list. In 1844, a British officer named Henry Yule published a short account in the Journal of the Asiatic Society of Bengal. He described bridges in the rainforests of northeast India, bridges grown from living tree roots. He wrote about them with clear astonishment. The bridges he described are still standing today. They are built by the Khasi and Jaintia peoples of Meghalaya using the aerial roots of the Ficus elastica, the rubber tree. The technique is called Dujiangyan. Builders guide the roots of young trees across a bamboo or palm scaffold, directing them toward the other bank over years, sometimes decades, until the roots reach the other side and take hold. Then the scaffold is removed. The roots remain. And here is the detail that changes the entire category. The bridge does not stop there. Where 2 roots press against each other, they fuse permanently. The technical term is inosculation. Think of it like a scar. The more stress the joint experiences, the denser the tissue becomes. The more people cross the bridge, the stronger the contact points grow. Every crossing is, in a small and measurable way, an act of maintenance. In 2019, Professor Ferdinand Ludwig at the Technical University of Munich led the first comprehensive scientific survey of these structures. His team documented 74 living root bridges across 2 districts in Meghalaya. His conclusion was direct. These are structures that modern bioengineering has been attempting to replicate since the study was published and has not yet achieved at comparable scale. Some of these bridges are estimated to be several hundred years old. The exact age is difficult to confirm. Dendrochronology methods are limited on root structures. But the bridges Yule wrote about with astonishment in 1844 are still growing, still carrying people, and still getting stronger. No other bridge tradition on Earth produces this, and the next one does something equally impossible, but it is made of grass, not roots, and every single year it is cut loose and falls into a gorge. Every June, 4 Quechua communities in the Peruvian Andes gather at the edge of a gorge. The Apurimac River runs 30 meters below. Spanning it is a rope bridge, 28 meters long, woven entirely from ichu, a tough Andean grass that grows on the surrounding plateau. They study the bridge for a moment. Then they cut it loose. The old bridge falls into the gorge. And over the next 3 days, using no modern tools, no machines, and no materials that weren't available to their Inca ancestors, roughly 1,000 people from 4 communities rebuild it from scratch. New cables, new walkway, new handrails. Everything replaced, everything hand-woven, everything finished in 72 hours. The Quechua is a functioning bridge. People cross it. But here is the detail most accounts leave out. A modern metal bridge already exists nearby. These communities do not need this bridge for transportation. They rebuild it anyway. which means what they are preserving is not the bridge itself, it is the knowledge of how to build one. At its peak, the Inca rope bridge network stretched across approximately 200 suspension bridges throughout the Andes, a connected infrastructure that allowed people, messages, and supplies to move across terrain most empires would have found impassable. Today, Quetzalcoatl is the last one still built and maintained using the original method. When UNESCO inscribed the annual renewal ceremony in 2013, it was partly because the organization recognized what disappears if the community stops. Not just a bridge, but a complete and irreplaceable body of structural knowledge that exists nowhere else. The decision to keep rebuilding is deliberate. The communities know exactly what they are doing, and the technique itself is what they have decided is worth the labor. The next bridge has been standing for 2,000 years without being rebuilt once. The reason it does not need rebuilding is stranger than the reason this one does. And for most of the 20th century, researchers had the explanation completely backwards. For most of the 20th century, if you examined a sample of ancient Roman concrete under a microscope, you would see something that looked like a flaw. Scattered through the hardened gray matrix were bright white chunks, irregular, uneven, clearly different from the surrounding material. The accepted explanation was simple: poor mixing, workers who had not properly incorporated the lime, an imperfection in the manufacturing process, not a feature of it. The January 2023 study from MIT and Harvard showed the opposite was true. Those white chunks are called lime clasts. They are reactive. When a crack forms in the concrete and moisture enters, the lime clast nearest to the fracture begins to dissolve. The calcium it releases migrates into the crack, travels along the fracture surface, and reprecipitates as calcium carbonate, a mineral that fills the fracture from the inside out. Within weeks of cracking, the concrete begins to repair itself. Think of the lime clasts like aspirin tablets embedded in the material. The crack is the trigger. The moisture is the water. The tablet dissolves and treats the problem from inside. The previous explanation, poor mixing, was not just incomplete, it was the direct opposite of correct. The feature researchers spent decades calling a flaw was the most sophisticated part of the entire design.
Here's what that means in practice. Roman harbor structures, submerged in the Mediterranean for 2,000 years, are measurably stronger than when they were built. Modern Portland cement, the global standard today, begins failing within decades in marine environments. Same seawater, completely opposite outcome. In 2023, the same year the MIT study was published, a company called SilicaX placed 4 concrete slabs made from the Roman formula into Long Island Sound in New York, not to protect them from seawater, to place them in seawater and measure whether they did what the MIT study said they should. The U.S. Army Corps of Engineers has proposed the same formula for coastal infrastructure. Why did we stop using Roman concrete for 15 centuries? Not because the formula was hidden, because Rome fell. The trade networks that distributed pozzolana, the volcanic ash essential to the formula, collapsed. The builders who understood which ratios worked were scattered. The knowledge survived in the structures. What did not survive was the written explanation of why it worked. The test results from Long Island Sound are not yet published, and understanding exactly why the self-healing mechanism works took 2,000 years. The next Roman structure gave modern engineers a different kind of problem entirely, one that required a computer to confirm what a Roman mathematician had already decided in 120 CE. If this kind of evidence is what you come to YouTube for, subscribe. This channel covers exactly this, one structure at a time. The next 3 entries are the ones that changed how engineers think about what we are building right now. Stand at the base of the Pont du Gard and look up. 3 tiers of arches rise to nearly 49 meters above the Gardon River. The limestone is warm, golden in afternoon light, and the blocks fit together so tightly that the joint lines are almost invisible. There is no mortar between those blocks, not a single drop. Every stone holds because of gravity and precision alone. The Pont du Gard was built in the 1st century AD to carry water 50 kilometers from a spring near Uzay to the Roman colony of Nîmes. Its 3 tiers and its height were impressive achievements, but the most demanding engineering on the entire project was invisible. It was the slope. Across 50 kilometers of uneven terrain, including a mountain river valley and a 49-meter bridge in the middle, Roman surveyors maintained a descent of exactly 25 centimeters per kilometer. That specific gradient is what made gravity do the work. Too steep, and the water would erode the channel floor. Too flat, and the water would stop moving altogether. 25 centimeters per kilometer is the number that makes the whole system function, and it had to be held consistently across the full distance. To put that in proportion, maintaining that slope across 50 kilometers is equivalent to tilting a football field by just 1.5 millimeters from one end zone to the other, while building it across a mountain gorge, using a water level and a plumb line. The tools Roman engineers used, the groma for direction, the korobates for slope, are documented. What continues to impress engineers who study the structure today is that the precision achieved with those instruments across that distance and that terrain remains extraordinary by any standard of measurement. The blocks have shifted slightly over 2,000 years. One section permanently deformed due to the heat expansion of stone. The bridge bent. It held. It has held for 20 centuries since. One detail about the next bridge will change how you read everything else on this list. It was built in 1650, has 5 separate functions, and the name of the architect who designed it was never recorded.
In 1650, Shah Abbas II stood in a central pavilion on a bridge spanning the Dujiangyan River in Isfahan, looking out over water that was not moving the way a river normally moves. The water level was higher than it should have been. The bridge itself had raised it, and the fish below were breeding in a current that the bridge's own gate system had oxygenated, a detail that appears in the historical accounts of the period and is still confirmed by the structure's architecture today. This is not a metaphor for elegant design. This is the engineering. The Khaju Bridge has 23 arches. It was built under Shah Abbas II of the Safavid dynasty, spans the Dujiangyan River, and has functioned continuously since the year it was completed. It is, by every account, a beautiful structure. Beauty is the least interesting thing about it. Its first function is the obvious one. It is a bridge. People cross it. Its second function is a dam. Sluice gates built into the arches could be closed during dry periods to raise the river level by up to 6 meters, creating an artificial lake upstream. Open them, and the water releases. The bridge controls the river. Its third function, royal viewing platform. The central pavilion was designed specifically for the Shah to observe the artificial lake the bridge could produce on demand. A lake that existed only because of the gate system beneath where he stood. Its fourth function, water treatment. Historical accounts record that the motion of water passing through the sluice arrangement oxygenated the current, and that fish were deliberately bred in that oxygen-enriched flow. The bridge was, in effect, maintaining the river ecosystem downstream of it. The fifth function is disputed. The arch geometry of the Khaju Bridge produces acoustic amplification in specific chambers beneath the structure. Certain chambers enhance a human voice to a degree that researchers have noted and documented. Whether the architect designed for this property intentionally, or whether it emerged from the geometry without deliberate intent, has not been resolved. Acoustic engineers studying the bridge have not reached a settled conclusion. But here is the angle that changes how you read the rest of the bridge's design.
If those acoustic chambers were intentional, and the engineering precision demonstrated across the dam, the oxygenation system, and the royal viewing platform suggested that precision was available, then the bridge that controlled the river, raised and lowered the water level on command, and maintained the fish population below, also gave its builders something else entirely: the ability to conduct conversations that appeared public but could be heard privately by positioned listeners in specific chambers across the bridge. The most public gathering space in Safavid Isfahan may have contained a listening architecture that was invisible to everyone who used it. Whether this was deliberate or accidental is not documented anywhere. The acoustic properties are measured and confirmed. The intent is not. But it is worth noting the person who designed a structure with 4 confirmed engineering functions and 1 disputed surveillance function in 1650 left no name behind. 5 functions, 1 bridge, no name attached. And one of those functions may have been designed to ensure the most powerful person on the bridge always knew what was being said within it. The next entry has no architect at all. It was designed by observing a river for long enough to understand it, and it has been running itself without any mechanism for 2,200 years.
In 256 BCE, a governor of the Qin state named Li Bing was handed a problem that had been destroying the region for generations. The Min River flooded catastrophically every wet season, washing out farmland, displacing communities, and making the Chengdu Plain nearly impossible to inhabit reliably. During the dry season, the same land suffered drought. The obvious answer was a dam. Li Bing did not build a dam. Instead, he spent years observing the river, not planning against it, observing it. He studied how the water moved around bends, how centrifugal force pushed sediment toward the outer bank, how the river's own behavior changed seasonally. And then he built a system that used all of that behavior against the problem itself. The central feature is called the Fish Mouth Levee, a long tapered stone island built directly into the river that splits the flow into 2 separate channels. During flood season, the outer channel, wider and naturally lower, carries 80% of the excess water away from the farmland. During dry season, that ratio reverses. 80% of the flow moves into the inner channel, which feeds the irrigation network. No gates, no mechanisms, no human decision required. The river regulates itself using its own physics automatically every season. Think of it the way a traffic roundabout works. It uses the momentum of the vehicle rather than a traffic light to route it correctly. Dujiangyan does not stop the river. It shapes the conditions under which the river makes the right decision on its own. That principle, using the environment's own properties rather than resisting them, runs through every entry on this list. The last one takes it further than any of them. It is a dome. It has been standing for 1,900 years. And when modern engineers ran a computer optimizer to find the theoretically ideal design for a structure of its dimensions, the software arrived at almost exactly what a Roman engineer had already decided in 120 CE.
In 120 CE, the Emperor Hadrian completed a building in Rome that contained a dome no one has successfully replicated in unreinforced concrete in the nearly 1,900 years since. The Pantheon's dome is 43.3 meters across. No steel reinforcement, no modern composite materials, concrete, geometry, and one decision that structural engineers would only formally confirm 19 centuries later. The decision was this: the Romans did not use the same concrete mix throughout the dome. At the base, they used travertine, one of the heaviest aggregates available. Moving upward through the structure, they switched progressively to lighter materials: brick, then tuff, then pumice, volcanic foam, one of the lightest naturally occurring stones on Earth. By the time the dome reaches the open oculus at its peak, the concrete is roughly 1/3 the weight of the concrete at its base. The result is a dome that becomes progressively lighter as it rises, reducing the compressive forces precisely where the structural geometry is most vulnerable. The dome does not fight gravity. The geometry and the material work together, each section carrying only what is best suited to carry. Here is the detail that changes how you read this. When structural engineers in the 21st century modeled the Pantheon's dome in computer optimization software, running thousands of iterations to find the mathematically ideal distribution of weight for a dome of this exact geometry, the software produced an aggregate distribution close to what the Roman engineers had already implemented. Not approximate, close to the theoretical optimum. A computer running optimization algorithms arrived at almost exactly the same answer as a Roman engineer who decided this in 120 CE. Using mathematics developed by hand, physical intuition about compression, and a material they had been refining for centuries. The engineer who specified which aggregate to use at which height left no written explanation of why. The architect's name is not recorded. The dome has stood for 1900 years without a single reinforcing rod. And the reason it has stood, confirmed by a computer that didn't exist until 17 centuries after the dome was finished, is that whoever built it understood compression geometry and material distribution at a level that took modern structural science until the 21st century to formally describe. 7 structures, 7 different civilizations, no documented contact between any of them on these specific design problems. And running through all 7 is a single thread, one that becomes visible only when you look at them all together. None of these systems work by fighting what surrounds them. Roots grow toward water and fuse under pressure, adding mass where the bridge needs it most. Grass rope yields to wind rather than resisting it. Lime clasts absorb moisture and use it to seal what cracked. Stone blocks hold by their own weight and geometry alone. A river is split by the shape of an island and steers itself into the correct channel seasonally, automatically, without intervention. Sluice pace use the river's own level to raise it further. A dome becomes lighter as it rises so that gravity itself distributes the load correctly at every height. The official explanation for why ancient structures survive longer than expected is usually given as superior craftsmanship or quality materials. What the peer-reviewed evidence from the last 5 years shows is something more specific than that and more interesting. Several of these systems are not merely surviving, they are improving, growing denser, growing harder, growing more fused with each passing season. That is not a property of craftsmanship, it is a property of design. The 2023 MIT study did not recover a formula that had been hidden. The 2019 Meghalaya survey did not discover bridges that no one knew existed. Both found knowledge that had been applied for centuries, confirmed by the structures themselves, but never formally described in terms that modern science could evaluate. The knowledge was always there. What was missing was the question, which raises one that is genuinely open. What else are we currently calling an imperfection that is actually the mechanism? What else have we been dismissing as a mixing error, a structural irregularity, or an accidental property when it is in fact the most important part of the design? That question is not rhetorical. The lime clasts were called a mistake for a century. They were the answer. Which of these 7 surprised you most and why? Tell us in the comments. We read every one.